let's call this the HbO2, which HB stands for hemoglobin O2 oxygen. So this is actually what we call oxyhemoglobin. Okay, you okay with that? Oxyhemoglobin. And we're going to call this a dissociation curve. So we have here, if we're looking at percent saturation of oxygen and under varying partial pressures of oxygen, which one of those is dependent, which one is independent? Does the amount of oxygen in the atmosphere or in the blood depend upon how much binding there is, or does how much binding there is depend upon how much oxygen there is? Binding depends upon oxygen, right? So here, we draw this graph here, this one.
Larry, do you have your fat?
That, this is going to be percent HbO2, so percent oxyhemoglobin. That makes sense? And this down here is going to be partial pressure of oxygen. You okay with that? So let's put some numbers on here. This is easy to do because how many can one hemoglobin carry? 4. So we'll either do 1, 2, 3, or 4. So that's 100% saturated when it's carrying 4. 75%, right? 50%, and 25%. You okay with that? PO2. This would be what? 0, I guess, here, huh? And what's the most we see in alveolar air that we saw? 100. Yeah, about 100 millimeters of mercury. So this is millimeters of mercury. So that makes this here then 50, there, 75. Okay. Is that all right? What partial pressures, what are the 2 partial pressures of oxygen that hemoglobin is likely to encounter? So I guess what I'm asking is what's the partial pressure of oxygen in the alveolar air, and what's the partial pressure of oxygen in interstitial fluid at rest? 100, right? This was the partial pressure of oxygen in alveoli, right? And 40 was it? That's the partial pressure of oxygen in tissues. Okay. And now we just need to know, okay, what does this look like? It could be linear, right? We could have a curve that looked like this. More oxygen, more hemoglobin. That would mean that if we drew a straight line like this, that would mean that the affinity never changes. Does that make sense? That's what it would mean. I mean, every time it's just constant. The affinity's constant. Add twice as much oxygen, get twice as much oxyhemoglobin. 3 times as much oxygen, 3 times as much oxygen. 4 times as much oxygen, 4 times as much oxygen. Does that make sense? Do you think sometimes, is the local environment of this protein changing as I add oxygen? Yeah, do you think that maybe the affinity could change? That, like, here it is at 0, it has a particular affinity. Do you think if this binds oxygen here, that might affect the affinity of these ions over here? Yeah, it could be, right? And probably likely will, because it might change the shape of things. Or certainly, the more oxygen you add, you're changing the local environment. You might increase the affinity, you might decrease the affinity, but you could affect the affinity. Everybody believe me on that? All right. So, this is what it looks like. I'm going to have to cheat here. That's what it looks like. So that is kind of S-shaped, right? It has, there's very little oxyhemoglobin here when there's very little oxygen, but the more oxygen you add, the more oxyhemoglobin you get. The more oxygen you add, the more oxyhemoglobin you get, until you get to a point. What's that point? That point's about right here, where I start saying, I don't really, if hemoglobin has 3 oxygens on it already, it doesn't really want to take the 4th one. It will, right? So what are we happening? Increasing affinity, increasing affinity, increasing affinity, decreasing affinity this way. So once if it's got 1, it likes 2. If it's got 2, it likes 3. But as soon as it gets 3, what does it say? I don't really want any more. But we can make it take more if we do what? Put more oxygen out there before it takes, like pushing it on it, right? To do it, and it will do that. And that's what it kind of looks like. So this is kind of the sort of curvilinear oxygen hemoglobin dissociation curve under normal homeostatic conditions in the body. It looks like this. Now we can answer the question, under the different conditions of oxygen that we have in the pulmonary circuit versus the systemic circuit, how much oxygen will hemoglobin carry? So we have them on here, right? So if the tissues, like this, it's about right there, the lungs, it's about that. Okay? So what does this mean? This means when my blood goes to the pulmonary capillaries, here, and the partial pressure of oxygen in the alveoli is 100, my hemoglobin will be 100% saturated. You with me on that? That makes sense, right? Because what happens if the lung blood gets oxygenated? And what we want it to carry as much as it can. So under normal resting conditions, if the partial pressure of oxygen in the air in the alveoli is 100%, hemoglobin will be 100% saturated. If it's 100 millimeters of mercury, it will be 100% saturated. Then where does it go? It goes to the body. And when it gets to the body, what's the partial pressure of oxygen in the tissues? 40. So what's the affinity of hemoglobin there? Let's come up here. Boom. It only likes to hold how much? 3. So what's it going to do? Release 1 of them. And where's this going to go? This is going to go to the tissues. So this is normal exchange. So under resting conditions, your blood will release a single oxygen molecule per hemoglobin into the interstitial fluid, and that's what your cells will use to do cellular respiration. Now this means, remember we talk about, and I probably made this point, or I usually try to make this point when we talk about blood in veins being deoxygenated. That's really a misnomer, isn't it? Because here, it's under normal resting conditions, blood in veins is 75% oxygenated. Right? It's oxygen, it's less oxygen in the veins than in the arteries, but it's still oxygenated.